Welcome, everyone, to The Explainer, and a massive welcome to all my first-year computer science students joining us today. You are at the very beginning of an absolutely fascinating journey into algorithmic thinking, and today we're tackling your foundational first step, bubble sort. My goal here is to break down these abstract concepts into clear, visual steps, so you're not just memorizing code, you're truly grasping the underlying logic. This is where we learn how computers literally organize the world.
Here's our syllabus for today's Explainer. We've got a great roadmap to take you from pure theory all the way to real-world practice. We'll cover algorithm basics, the soda bubble analogy, step-by-step mechanics, practical applications, and finally, some common beginner mistakes.
Okay, let's dive right into this with Section 1, Algorithm Basics, Defining Bubble Sort.
So at its core, bubble sort is a really simple, comparison-based sorting algorithm. The main goal here is to take a completely chaotic, jumbled collection of data and organize it into a neat ascending or descending order. And how exactly does it pull this off? Well, through local swaps. Basically, it repeatedly steps through the list, looks at adjacent elements, right side by side, compares them, and swaps them if they happen to be in the wrong order. It's a highly localized way to look at a problem. You aren't looking at the whole array at once, you're just looking at the two items right in front of you.
Moving on to Section 2, the soda bubble analogy and visualizing our data.
Before we get bogged down in the raw logic and the loops, we absolutely need to visualize this data in motion. I want you to picture a tall glass of soda. What do the carbonation bubbles do? They slowly rise to the surface, right? And this brilliantly illustrates exactly how the algorithm gets its name. As our code runs, the absolute largest elements in our array act exactly like those soda bubbles. Through those repeated local swaps we just talked about, the largest values slowly, but very systematically, bubble up to their correct positions at the very end of the list. And once a bubble hits the surface, meaning the largest number reaches the end, it just stays there, totally locked in place.
Now, what's really interesting about this next slide is Section 3, step-by-step mechanics and how it actually works.
This is where we translate that visual of the rising bubbles into rigorous logical steps. Think of this as the actual engine of the algorithm, and we can break it down into 5 distinct phases. First, we iterate. That means we start at the very beginning of our array. Second, we compare. We look exclusively at just those first 2 elements. Third, we swap. If the first element is bigger than the second one, they trade places. Fourth, we move forward. We shift our focus to the next overlapping pair and repeat that exact same comparison. We keep doing this until we hit the end of the line. That right there completes one full pass. By step 5, repeat passes, that largest element is now sitting pretty at the end of the array. So we loop this entire process, repeating it for all the remaining unsorted elements until the whole list is perfectly ordered, the whole shebang.
So, looking at those 5 steps, you might be sitting there thinking, wow, this is elegant. This is super easy to write. If it's literally that simple, why on earth don't we use it for everything? It's a really great question. Why isn't bubble sort running the massive databases at huge tech companies? Well, to answer that, we really need to look at when it's actually appropriate to deploy this tool.
Which brings us to Section 4, practical applications, and when to actually use bubble sort.
Let's shift our focus from the purely theoretical realm into pragmatic, real-world engineering. Because bubble sort actually has specific, highly effective niches. First up, educational purposes. It's the absolute gold standard starting point for computer science education, mostly because it just so perfectly demonstrates algorithmic loops and swaps. Second, nearly sorted data. If an array is already mostly in order, bubble sort can actually be incredibly fast. Third, memory constraints. Now this is absolutely crucial. Bubble sort is what we call an in-place algorithm. That means it requires almost 0 extra memory to run. It doesn't need to copy your list to a whole new location. It sorts the data right where it sits. And finally, small data sets. For lists with just a handful of items, the sheer simplicity of bubble sort is sometimes preferred over much more complex algorithms that bring a ton of overhead.
But hey, it's not just a classroom toy. Out in the wild, you will actually see bubble sort used in specialized graphics hardware. Why? Because in certain hardware environments, that swap operation we talked about is extremely cheap to execute computationally. Plus, you can use a single pass of a bubble sort as a super quick check to verify if a list is already sorted. Think about it. If you do one full pass and make 0 swaps, boom, you immediately know your data is perfectly in order.
Let's look at Section 5, common beginner mistakes and the traps you definitely want to avoid.
As first-year students, you are absolutely going to write this code. And you know what? You're going to make mistakes. It happens to all of us. But I want you to burn this quote into your memory before you submit your very first assignment. Never forget, unoptimized bubble sort on a massive data set is a beginner's trap. So the crucial point here is that you must understand the scale of your data. Because bubble sort relies on nested loops, literally passing over the data again and again and again, the time it takes to complete grows quadratically as the dataset gets larger. Basically, it becomes extremely slow, extremely fast.
Here are the specific bugs you're almost certainly going to encounter. First, like we just touched on, inefficiency. Throwing this at a massive dataset is a critical error. Second, unnecessary passes. A really common beginner mistake is forgetting to stop the algorithm early if no swaps happen during a pass. Think about it. If you go through the entire array and don't swap a single thing, the list is already sorted. But an unoptimized bubble sort, it's just going to keep running blindly. And finally, indexing errors, specifically the absolutely dreaded off-by-one error. When you're comparing the current element to the next element, what exactly happens when your current element is the very last item in the array? Well, there is no next element, so if you don't properly adjust your loop boundaries, your program is going to crash looking for data that simply isn't there.
Which leaves us with a pretty fundamental programming challenge. We know for a fact that if a pass happens with 0 swaps, the list is completely sorted. So for your next assignment, I really want you to think about this. How can we optimize this algorithm so it knows exactly when to stop early? How might you introduce a simple flag in your code to track whether a swap occurred, transforming your standard run-of-the-mill bubble sort into a truly optimized bubble sort? Think about how that single tiny addition completely changes the efficiency of everything we've looked at today. Thank you so much for joining me for this explainer, and happy coding.